Hello, my name is Terence Broad, and in collaboration with Sebastian Burns, Simon Colton, and Mick Grayson, I'm very happy to present to you today our paper, Active Divergence with Generative Deep Learning, a Survey in Taxonomy. In this talk, I'm going to give an introduction to generative models and active divergence. The bulk of the talk, I'll be giving a step-by-step presentation of our taxonomy and all of the methods that we've included in our survey. And then at the end, we're going to discuss some of the applications of active divergence techniques and future research directions, and we'll finish with some concluding remarks. So, deep generative models. Deep generative models are neural networks that generate data. They can generate data such as images, audio, symbolic music, text, video, etc. There's active development in many research communities, so not just machine learning, but also computational creativity, computer graphics, audio-digital signal processing, computer-human interaction, etc. They are capable of producing artifacts of high cultural value, and because of that, there's high levels of interest from creative practitioners who want to use this and do use it in their artistic practices. So here are two examples of two of the state-of-the-art generative models. On the left is StyleGAN2, which is the state-of-the-art for image generation, and you can see it generates photographic images here, and we're going to be seeing a lot of examples that uses StyleGAN2, so you're going to be seeing lots of images of faces. And then on the right we have Jukebox, which is a generative model for making audio. There are other generative models such as GPT-3 for text, etc. When we train a generative model, we have a target data distribution P, which is our training data. We have a network with parameters W, and the goal of training is to optimize the network parameters using stochastic gradient descent so that the results from the model best approximate the target data distribution. And so in doing this, we're minimizing the divergence between the target distribution P and the approximate distribution P prime. And the goal is to get the divergence as close as we can to zero between these two distributions. So if we look at these two diagrams, on the left we have a generative model, a feed-forward model, that is initialized with random parameters. On the right is a trained model, so once we've trained it on the data, we found the best set of parameters that best approximate the data distribution P. In the distribution view, on the left is our target distribution, and after training, in the middle, we have our approximate distribution P prime, which is colored green. And on the right, we can see these two distributions overlaid. So the generative model is not always going to perfectly reproduce the distribution. It might miss out modes, but it also might generate things that don't lie in the original data distribution. So what is active divergence? Well, this term was introduced by my co-authors, Sebastian Burns and Simon Colton, in a paper from last year's ICCC titled Bridging Generative Deep Learning and Computational Creativity. And they define active divergence as using generative deep learning in ways that actively diverge from the training data. And this is an important distinction to make because all of the standard approaches for training generative models are to minimize the divergence from the training data. And by pursuing active divergence, we can go beyond simply imitating the data, and we can start using these highly powerful neural networks for generating novel outcomes. Active divergence can be achieved either through searching, training, fine-tuning, or making post-training modifications to the models, and these are the things that we're going to be discussing in our survey. So why do we want to pursue active divergence? Well, approximating a data distribution on its own is not really a creative act. Simply imitating the data that you have is not very creative. That isn't to say that deep generative models can't be used in creative systems, but the act of imitation on its own is not particularly creative. So active divergence methods are really important for facilitating creativity. They allow for novelty generation, but not just generating novel samples, generating novel distributions of samples, of complete novel outcomes. And it allows existing models to be adapted to unseen domains. So the motivation of our survey is to collate all these known methods into one place. We've formalised and grouped these methods based on underlying principles into our taxonomy, and we've done this to provide a resource for future machine learning and computational creativity researchers. Another important thing that we want to do in this survey is draw links between what's been going on in artificial intelligence research and what's been going on in experiments by artists and other practitioners who are also using these generative models. And we've gone to great pains to give credit to all contributions regardless of where they've been disseminated. So in our paper we've cited blog posts, GitHub pages, Colab notebooks, and even social media posts, because really important breakthroughs have been disseminated on all of these platforms. So this is our taxonomy of active divergence methods. We've broken it down into 8 categories. These are novelty search over learned representations, novelty generation from an inspiring set, training models, training without data, divergent fine-tuning, network blending, network bending, and model rewriting, and I'll be discussing these in order. I'm not going to be giving a comprehensive overview of everything in the survey. I'll just be giving illustrative examples for every one of these methods that we're discussing. If you want a fuller account, then you'll have to read the paper. So, the first technique we're going to discuss is novelty search over learned representations. So here, we're training a generative model in the standard way, where we're trying to minimize divergence from the generated distribution from the target distribution. However, there is always going to be some degree of divergence with high-dimensional data such as images or music. So, taking that into account, Kazachi et al. Train a sparse autoencoder on the MNIST handwritten digit dataset, and then after training, they search the entire space of generated outputs and find the results in P prime, the approximate distribution, that aren't present in the target distribution. And this subset of samples is in itself a normal distribution of results. So in this diagram, you can see that the subset of, we've color-coded in orange the subset of P prime that isn't P prime, the approximate distribution, that isn't present in the target distribution P. So the next techniques we're going to discuss are ones that generate novelty from an inspiring set. So here we're training a model from scratch, using a training data set, but this data set we're not trying to imitate it per se, but we're using it for inspiration, which is why we've called this an inspiring set. Because the goal is novelty generation. The 2 methods that we're going to discuss both rely on labelled classification datasets. However, that doesn't necessarily need to be labelled, and there's scope for this to be done in an unsupervised fashion in the future. So, building on the work that we've just seen, Cherty and others train a class conditional model with extra holdout classes. So again, they're working on the MNIST digit dataset. So you've got the 10 classes for the 10 digits, 0 to 9, but then they add extra classes, and after training, they can sample from those classes, and these classes encapsulate the novel samples that lie outside the true distribution. So in this case, we don't need to be doing any searching over the model. We can just sample using the holdout class labels, and we'll get novel outcomes. The next technique we're going to discuss is creative adversarial networks. So Elgamal and others take inspiration from the GAN framework. But here, they're training the generator to maximize the likelihood of art. So they're training this on a painting, the WikiArt dataset of digitized paintings. So we're maximizing the likelihood of generating a painting, but we're diverging as much as possible from any of the existing styles of paintings that are in this labeled dataset. So again, if we look at the distribution view, our novel distribution U is trying to fit the original training data, but diverge from any of the existing styles. So everything generated by this model is novel to some degree, but it is still inspired from the original training distribution. A technique which is very commonly used by artists, but not really discussed much in academic literature, is this practice of chaining models together. So they will combine lots of models trained on different data sets, usually trained on custom data sets of data collected by the artists themselves. And the artists might retrain and retrain these models over and over again until they get the desired results. So techniques that might be chained together are unconditional generative models, such as a GAN, but then you also might use translation models. So in the case of images, you'd be using something like pix-to-pix or cycle-GAN, and these may be chained multiple times, one after the other. And other techniques like style transfer, super resolution, and network bending, which we're going to discuss in a bit, may also be used in this process. The next method in our taxonomy is training without data. So here we're starting from a network with randomly initialized parameters, and we train the model without any data, and in doing so we're almost certainly going to find parameters that produce a novel data distribution. The current methods rely on the dynamics between models to provide these gradients that are used for training. And we've got two methods to date, which are multi-generator dynamics and generation via communication. So in some of my previous work, I trained two generator networks in a framework that takes inspiration from the GAN framework. But instead of a generator trying to reproduce data, we have two generators that are trying to copy each other. They converge into producing quite simple forms, but a trick to get them to produce diversity in their output distributions was to get these two generators to compete to produce the most colours in their output batches. A different approach is generation via communication, or maybe we should call it communication via generation, because we have two networks that are communicating to each other via a generative medium. So Joel Simon in his work Dimensions of Dialogue uses a pair of networks, one generator and one generator that generates images based on word vector embeddings of a corpus of text or of sentences. And then another network looks at those images and tries to get back what the original word vector would be. And in doing so, you can produce a distribution of images that represent words. The next category of techniques we're going to discuss are divergent fine-tuning techniques. So here we're starting from a pre-trained model, and then we're fine-tuning the model to learn parameters that produce a novel distribution. One of the advantages of these techniques is that fine-tuning models performing transfer learning is very fast because we're starting from robust initial parameters. And for instance, in the case of something like StyleGAN, it's trying to train a model like that from scratch is prohibitively computationally expensive. So people will often start with a pre-trained model. Another advantage of these techniques is it allows for the creative transformation of existing data domains. So you can kind of riff off an existing data set. And in our taxonomy, we've got 4 categories of this. So we have cross-domain training, continual domain shift, infusing external knowledge, and loss hacking. All of these techniques currently rely on some kind of human evaluation to select the best iteration of the model, but we believe in future that this could be automated. So the first method we're going to discuss is cross-domain training. So here we're starting from a pre-trained model trained on the one domain P, and then we're going to perform transfer learning to a new domain Q. However, if we stop halfway through, the parameters of the iteration of the model in this midway point can produce results that are a hybrid between these two domains. So as I was saying, a lot of people start, when they're training a StyleGAN model, will start with the default model of faces, and then they'll be training it on their own data set, and then they'll find that halfway through you get very bizarre and unexpected results. So on the left we have a hybrid between faces and beetles, and on the right we have a hybrid between faces and cats. Another approach which is related, but a bit more advanced, is to fine-tune the model on a continually shifting domain. So we're doing transfer learning, but the domain that we're training it on is constantly changing. And so Malsom, I believe, pioneered this, and then making the series Strange Fruits, he steered the training process by adding in generated samples from previous iterations into the new target distribution. And by doing this, he's able to almost steer this divergent fine-tuning process and have a level of control over it. The next category of divergent fine-tuning is infusing external knowledge. So here we're not using any data, we're using an external model that's already been trained on a different data domain that we probably don't have access to. And then we're using that and trying to infuse some of the knowledge learned in this other network into our own network that we're starting off point. So Gal and others use the CLIP model, which is the contrastive language image pre-training model. And they use this to fine-tune a GAN based on user-defined text inputs. So again, here we're fine-tuning a style GAN, and then using text inputs, we can change the entire model to fit characteristics that we define in our text input. So here we're going from a photo to a cubist painting, and everything in the results will be changed in this way. The final method we're going to talk about is loss hacking for divergent fine-tuning. And here we're fine-tuning a model with a loss function that doesn't maximize the likelihood of data or maximize the likelihood of another network. So we're doing something quite different. We're kind of really hacking the losses, so to say. So in some of my previous work, I took a pre-trained GAN and I fine-tuned it by inverting the adversarial loss function. So instead of the generator maximizing the likelihood of generating the data that the discriminator would think the data is real, we turned it around. And so inverting it, we suddenly are maximizing the unlikelihood of the data, or what the discriminator would predict as being fake. And as you can see, we get these very uncanny images. And just one note I'd like to add. A lot of these techniques can result in mode collapse, and mode collapse is often seen as a failure state in deep learning. So that's when your generator collapses into just producing one single representation rather than an entire distribution. So normally this is something we'd like to avoid. However, that's been observed in a few of these techniques is that actually the process, the dynamics that lead to mode collapse can be really interesting, and the iterations of the model, the snapshot of the model just before mode collapse, can lead to very creative results. So I think in the context of creativity, mode collapse isn't necessarily something that we want to avoid, and it could be used for inspiration. So the next technique we're going to be talking about is network blending. Here we're generating hybrid data distributions by blending models together, trained on different data domains. And here we've categorized this into two different kinds. We've got blending the predictions of the models, so the outputs of the models, or blending the parameters of the models. So when we're blending predictions, we're blending the output. So here, Atkin and Grierson present a real-time interactive text generation interface where lots of LSTMs that do next character prediction trained on different corpuses of data can be combined together. And so the predictions of the next character can be customized in this interactive framework. Ooh. The next category is blending the parameters. So here we're actually blending the weight parameters of the models. And this only really works effectively if models have been transfer learned from the same original source. So we have two networks, one trained on P, one trained on Q, and then we can combine their parameters in different ways. So we can interpolate on all the weights, we can swap layers in and out between the different networks, or we can do kind of graded interpolation, which is a generalization of the two. So this is a very good demo of interpolating the weights of 5 different models trained on different data domains, and they've all been transfer learned from the StyleGAN model of faces and trained on different data domains, which again are faces, and this really shows the power of how you can interpolate and have very high degrees of control in blending these different data domains together. Cool. The layer swapping technique allows us, instead of just blending things overall, we can have more control over whether we want the high level features of one model with the low level features of another. So in this example, we have photographic faces and then an ukiyo-e model. And then when we blend them together, we can either get very photographic images that have the spatial structure of ukiyo-e datasets, or if we do it the other way around, then we can get the spatial structure of normal faces, but with the lower level detailed characteristics of ukiyo-e models. And this technique was also used in a very popular tunification method, where a model was trained on Pixar, like Disney-esque characters, and then you can find people's identities in the StyleGAN latent space, and then you can find the tunified version of them. So the next technique we're going to be discussing is network bending. So here we're not making any changes to the parameters of the model. We're simply inserting extra layers into a pre-trained model that apply deterministic filters. And by doing this, we are changing the internal representations and therefore changing the output distribution. So these deterministic filter layers are inserted into the models, and this allows for the direct manipulation over the inner representations. So I presented this work in images at Evo Musart this year, and it's also been done in the audio domain. And as you can see, applying these filters in different layers gives us very different results. Also, in this network bending framework, we pre-analyze the models and we perform clustering on convolutional features to group them together based on the similarity of them, the spatial similarity of their activation maps. And once we've clustered them together in an unsupervised fashion, we find groups of features that are responsible for semantic properties of the generative process, and these can then be manipulated in tandem. The final technique that I'm going to discuss is model rewriting. So here we're making targeted changes to the parameters of a model trained on one distribution. And by making these very small targeted changes, again, we've changed the model, and then where the result is that we're getting a new distribution. So this can be done stochastically. So to make the artwork's neural glitch, Mario Klingerman took pre-trained models and then randomly altered the values of the weights, deleted the values, or swapped parameter values. And he did this in a random fashion, and then he would select the results that were most interesting, and that was how he made these amazing artworks. But this can also be done in a targeted way. So Bao and others, in a paper rewriting the rules of a generative model, use a copy-paste interface to make targeted changes to the rules of a generative model. So the example on the right is that they've taken a model that generates churches, and then using an almost Photoshop filter-like technique, they say, okay, I'm going to replace the church tower with a tree, and then they optimize the model using stochastic gradient descent, but they freeze all of the layers apart from one, so they're only changing one layer at a time. And once they've performed this, the model gets rewritten, and now every church tower now has trees growing out the top of it. The final technique we're going to discuss is the combinets framework. So here we're writing a new model using heuristic search in a targeted fashion, but we're using parameters from a number of pre-trained models. So we're combining parameters from lots of models in a targeted way, and we're doing this to account for a new mode of generation. So the example given in the paper is that, say we have a model that can generate horses and a model that can generate birds, but we want to generate a Pegasus, but we don't have any data of Pegasus, or we have a very limited number of data, so we have 1 or 2 images. Then we want to combine these models together so that we get the features for generating the wings from the birds, but also generating the bodies of the horses. And so we have a new model that generates Pegasuses. So that's the overview of our taxonomy. And now I'm going to discuss some of the applications of active divergence techniques. So novelty generation is an obvious one, but we think generating novel distributions and generating novel distributions that might have desired characteristics that we don't necessarily have data for is a really useful application of active divergence. We can see a lot of scope, and it already has been used in creativity support tools and in co-creation tools. And active divergence techniques allow us to recombine knowledge from learned representations and again adapt our models so that we can adapt them for domains where we don't necessarily have data for. And we also think this could be a benchmark for creativity. So some of the future research directions that can be pursued in active divergence. So the main one is evaluation of active divergence techniques. For the most part, there really is not much evaluation done. And what would be really good is if we had quantitative metrics that allowed us to really analyze the changes to distributions, the changes to models, and whether our results, how divergent they are, but not just how different they are, but also how have they changed, and is the change good or bad? Have we, has our model collapsed? Have we reduced the variation in the data, or have we increased the variation of the data? Is there a concurrency in change, or has everything just been scrambled up? So I think there's a lot of scope for developing metrics in order to better understand these techniques. And once we have these quantitative metrics, then it should be easier for us to automate qualitative evaluation and the hand selection and the hand selection of outputs that currently is used. And so looking forward, we can see these being used in autonomous creative systems. And some of the key things that would need to be present for that to be the case is being able to formulate and realize intentions with these models. And if a model was able to invent its own objective function and train a model from scratch, then that would be another key way where we could define these as being autonomous. And then looking forward for some of the possibilities for achieving active divergence with techniques that we've not necessarily discussed in this taxonomy. So I think there's a lot of scope for multi-agent systems, and multi-agent systems, we've seen a little bit of that in the training without data, but there's a lot more scope to improve that and develop this further. And also open-ended reinforcement learning could be very fruitful in achieving active divergence. So to conclude, we've compiled a comprehensive survey of active divergence methods, and we've generalized these and formalized these into our taxonomy. We've done this to provide a resource for furthering research in this area. We've highlighted applications and future research directions for active divergence techniques. So thank you for listening. You can contact me at t.broad@goal.ec.uk or @ToryBroad on Twitter. Thank you very much.